hydroxide ion. The upshot of which is that even though acid solutions are stronger oxidizing system than basic solutions, you can oxidize a lot of metals in basic solution because of their ability to form very stable hydroxide complex ions. This is such a case. The half part corresponding reduction is water converting the hydroxide ion as hydrogen gas is liberated. Remember, in sodium hydroxide solution, principal species inventory, sodium ions, hydroxide ions, water, that's it. So if you're going to make hydrogen, clearly it's hydroxide ion or water which is getting reduced. Which of these is the better acid? Which of these is the better of +1 oxidation state hydrogens? Acid-base chemistry all over again. Water is a much better acid than hydroxide ion. So water gets reduced. Now, oxidation of aluminum. If again, as always, you pay attention to the principal species inventory for the system you're considering, you will be successful in developing these half reactions. And if you don't pay attention to the principal species inventory, you have no chance. If aluminum, on being oxidized in 6 molar sodium hydroxide solution, is converted to this species, is there any difficulty in supplying the formulas for the other reactants which are necessary to form this species? Hydroxide ion, water, they're in there. Put them in. That's all there is to it. If you pay attention to the inventory, no problem. If you don't pay attention to the inventory, this is a total mystery. So, what we have written establishes material balance for this half reaction because we've paid attention to each component from a material standpoint. Remaining part is to establish charge balance. What we have on the board so far shows 4 moles total minus reactants, 1 mole total minus products. That means we got to have 3 moles electrons total for 4 moles negative on each side of the reaction arrow. Does that keep with the change in oxidation state for aluminum? Did you learn in 2045 or maybe even in high school chemistry that aluminum, which is a member of family 3A, develops only 1 common positive oxidation state? What is it? +3. So if aluminum 0 gets oxidized to aluminum +3, we've got to associate this with loss of 3 moles of electrons. Now, to couple these half reactions, we're going to have to take this half reaction, at least I think the simplest way to do it, and multiply it by 3, this one by 2. This is little more than simple arithmetic. After we do this, we can write the net cell reaction and answer the question for this redox system. What happens to pH as this redox reaction runs? Does the pH stay the same? Does the pH go up? Does the pH go down? Now you can do this by brute force. By brute force I mean, write the equation for the net cell reaction and see if it leads to net consumption of hydroxide ion or production of hydroxide ion. What will you find out? There's a net reaction for this system. lead to net consumption of hydroxide ion or production of hydroxide ion? What do you say? Not hard, is it? 3 times 2 will put 6 moles hydroxide ion as products. 2 times 4 will give 8 moles hydroxide ions as reactants. So what's happening to pH as this reaction runs? pH stay constant? pH go up? pH come down? Yeah. Because we're looking at net consumption of moles hydroxide ion. But you didn't have to write the equation for the net cell reaction to recognize that. Because this thing as it stands shows that per mole of water reduced, you're making a mole of hydroxide ion. 2 per mole, okay. And this as it stands shows that per mole of aluminum per mole of aluminum oxidized, you got to consume 4 moles of hydroxide ion. It means you're consuming more moles of hydroxide ion than you're making. pH has got to come down. Now there's another part attached to this, another question. That's part 5 of question 22. Or question 15, I mean. Why is it not the case that this is a water solution oxidation of aluminum? So why don't we make this? You recognize this is quite a basic solution? Can't make this in a basic solution. This is an acidic species. So, chapter 18 again. We're now going to take a look at a system which very much parallels this. This is the oxidation of chromite ion. For those of you who get to assignment 10 and 46 laboratory, you'll do this reaction. You'll oxidize chromite ion by hydrogen peroxide and convert the chromite ion to chromate ion. When hydrogen peroxide is reduced in basic solution, you turn it into hydroxide ion. Well, establishing material balance for this is pretty simple. There's a molecule of hydrogen peroxide, 2 H atoms, 2 O atoms, so 2 hydroxide ions produced. And 2 electrons required to establish charge balance. Now what about chromite ion? That's just a trivial name of sorts for this thing. Well, we call it this in the lab manual, so I'll call it that here, chromite ion. We'll learn in chapter 24 that this can be called diaqua or diaquo tetrahydroxo chromate 3 anion. Never mind that name for now. Tell me, when you look at this formula and recognize it to be a complex ion with a chromium atom to which are connected 2 water molecules and 4 hydroxide ions, 6 groups connected to chromium, might you reasonably speculate that this complex ion is octahedral? You probably didn't use the word coordination when you learned about this stuff in 2045, but you learned about properties such as sp3d2 hybridization, which corresponds to 6 atoms or 6 groups connected to a central atom. I'm sure you looked at models for octahedral species. Do you think the chromite ion looks like this? Where the red ones are representing the water molecules and the black ones are representing the hydroxide ions? Or do you think the chromite ion looks like this? You see the difference between this picture and this picture? We're going to draw these pictures extensively in chapter 24. You see this canted square? It's not like this. It's canted relative to the drawing surface. The purpose of canting the square is to get you to recognize that this square is not in the plane of the drawing surface. It's this way. The square piece of paper held this way. And up here is the top atom or group. And down here is the remaining atom or group to define the octahedron. Do you recognize that octahedral geometry is really pretty simple? Did you do that in 2045? There's only two principal bond angles for a species that's perfectly octahedral. What are these bond angles? 90, 180. In Chemistry 2045, did you talk about trigonal bipyramidal species? You did that, didn't you? With sp3 dehybridization for the central atom. You did that. And 5 surrounding atoms or groups. Is trigonal bipyramidal geometry simpler or more complex than octahedral geometry? Trigonal bipyramidal geometry, 5 peripheral atoms or groups. Octahedral, 6 peripheral atoms or groups. Which is the more complex geometry? This octahedral or trigonal bipyramidal? I'm just curious if you did this in 2045. Which is the more complex geometry? What are you going to think about to answer this question? Well, we just reminded you, looking at this octahedral model, there's 2 principal bond angles. 90, 180. How many principal bond angles for a trigonal bipyramid? How many? You draw pictures like this of trigonal bipyramids? For the in-plane species, where this is a canted triangle, because this is not in the plane of the drawing surface. It's this way. Well, if these atoms or groups, which are in the equatorial plane of this trigonal bipyramid, are all the same, then this bond angle is how much? 120. But this bond angle is how much? 90. And this bond angle is 180. This is a more complex geometry. 3 principal bond angles versus 2. Even though you only got 5 peripheral atoms or groups compared to 6. This is a simpler geometry. So for this simpler geometry, you realize that with the picture on the board, I've shown the 2 water molecules to be at a 180-degree angle with respect to each other. But for the model I hold in my hand, the like water molecules are at a 90-degree angle with respect to each other. I'll hold it like this if you prefer. Which do you think is probably correct? What's your horse sense tell you? Or don't you hang around with horses? No? What do you bet? If you had to make a bet, what would you bet? Come on, make a bet! 90-degree angle for the water molecules. How many bet that? 180-degree angle for the water molecules. How many bet that? Just about everybody bets that. Well, why didn't you tell me that when I asked you? So I hate to use these models. It fell apart. Is this more likely? It's what you told me. You're right. Why? That's always the question you got to answer in chemistry class. Why is this more likely than one we looked at previously? Well, water's a polar molecule. I agree with that. So, what about hydroxide ions? Ooh. Now, we don't usually apply the term polar to ions because they're like monopoles. They have a plus charge or a minus charge. Whereas a dipolar species is partially plus someplace, like for the hydrogen atoms of the water molecule, and partially minus someplace else, like the oxygen atom for the water molecule. Well, let me ask it this way. Does polar not refer to an electric character of a species? An electric character? Yeah. Talking about distribution of valence electron density. Which do you think is the more electric particle? The water molecule or the hydroxide ion? Which one? One's got a charge. The other one's a molecule. Hydroxide more electric? The answer to this geometry question lies in the orientation of the hydroxide ions in the octahedron, not the water molecules. Because if we have the hydroxide ions arranged in this square pattern, which you can see more easily if I hold a model like this, okay, the hydroxide ions are as far apart as they can be from each other. But if I put one of these hydroxide ions over here, then I'm going to have more 90-degree angles between hydroxide ions. Whereas here I have fewer 90-degree angles between hydroxide ions. Which means I'll have less, with this orientation of hydroxide ions, now I have less negative charge repulsion between and among hydroxide ions. That's why you get this geometry. And that's the kind of stuff you should have been talking about in 2045. How many did? Back to our analysis. Do you also realize that our model analysis, structure analysis for this chromite ion has shown us that we're starting with chromium covalently connected to oxygen in the parent ion. How many times? 6 times. But when we make the chromate ion, we've reduced this number of chromium-oxygen bonds to 4. Now, do you think it's more likely that in forming this from this, that all these bonds are going to break, all these groups are going to fall off, and then we're going to remake 4 bonds? Or do you think it's more likely that in converting this to this, 4 of these chromium-oxygen bonds will remain intact, and only 2 will break? Don't you think that's more likely than breaking 6 bonds and then making 4? Instead, let's just break 2 bonds, and there we convert that to this, while at the same time we've got to eject some protons. All right, let's take a look at this. Which of these bonds do you think? Water to chromium-3 or hydroxide ion to chromium-3? Which of these bonds do you think are stronger? There's a chromium-3 ion. From an ion-ion attraction standpoint, from a Coulombic standpoint, you think water molecules or hydroxide ions would stick more strongly to chromium-3? What do you think? Hydroxide? I bet that too. So, to turn this into this, we're going to break this bond, and we're going to break this bond. How do you think we're going to break these bonds? We're going to divide the electron pair in half? Would we break the bond, leaving the electron pair in the valence environment of chromium? No. You know that oxygen is more electronegative than chromium. So let's bet on breaking these bonds like this. Because when we remove electron density from chromium-3, are we not increasing the oxidation state of chromium? When we remove electron density, when we are removing electron density from chromium-3, are we not simultaneously increasing the oxidation state of chromium? Aren't electrons negative? So if we remove electron density, am I not going to make something more positive? Now then, let's look at one remaining and interesting aspect of this from an acid-base standpoint. Because what this is showing us so far is that in converting this to this, 2 water molecules are lost to the system, but hydroxide ions, which we have imagined to remain bonded to chromium-3, have lost what? They lost H+, didn't they? This chemistry is causing coordinated hydroxide ion. Hydroxide ions that are part of this complex ion. This chemistry is causing coordinated hydroxide ion to behave how? Huh? As what? A Bronsted acid. How about that? This coordination stuff, you can do all kinds of neat stuff with coordination chemistry. I mean, for example, do you think chlorophyll is important? You ever heard of chlorophyll? It's a coordination compound of magnesium plus 2. Chlorophyll assists green plants in converting atmospheric nitrogen to amino acids and proteins. Are these important to us? Huh? You know it's important to us. How about hemoglobin? Is that important? Hemoglobin is another complex species which is responsible for transport of oxygen throughout our system. Is that important? You know it's important. Back to this. We've now recognized that this chemistry is showing coordinated hydroxide ion to have the capacity as behaving as Bronsted acids. That's interesting. That means this coordination phenomenon is causing HO bonds to be weaker than they are as free hydroxide ions. Because free hydroxide ions are rarely showing the ability to lose H+ in water solution. Well, we've looked at a couple cases previously, if you remember such. Here we got a coordinated hydroxide ion. 4 of them, in fact, losing H+. Well then, tell me, as H+'s are contributed to a reaction system, like this system, during the course of a reaction, what always gobbles up these H+'s? What's the answer that's always right? The strongest base present in the system at high concentration or amount. Well, tell me, what is the strongest base in this system? Hydroxide ion. So, one of these has got to react with what to become this? 4 hydroxide ions, because 4 of these hydroxides that are coordinated are going to lose H+. So I got to have, in terms of moles, 4 H+ grabbers. And in this system, hydroxide ions are the best H+ grabbers. And when hydroxide ions grab H+, what do I make? Water. That wasn't too hard, was it? So up here we're going to write, in addition to what we already have, plus Water. How many moles? 6. We made 4 from H plus going to hydroxide ion, and 2 more from the moles of water that are kicked out of the complex. Now we had to think about a lot of things to develop this half reaction. It was not really all that difficult. Admittedly, we've not yet taken a look at structure analysis of complex ions. This is a peek to the future. But it does, I hope, remind you what you can achieve if you think about this stuff and pay attention to inventory. Okay. Part 7 of question 15. That's about as simple as can be. Look at the redox reaction table that's in the notes, table 2. Half reaction table, pardon me. Question 7 says, we're going to take nitric acid solution. I don't know, say 1 molar or 10th molar, who cares? And we're going to mix it up, say, with 10th molar ferrous sulfate solution. Or ferrous nitrate solution, or whatever. I don't know what I said in there. Let's take a look. Yep, ferrous sulfate solution. Well, if you pay attention to the system inventory, silver ions, nitrate ions, water, sulfate ions, water, and this. I'm charging you now with the responsibility to write a correct principal species inventory for this solution. Specifically, I want to know what ion in this solution contains iron. What is it? What is it? Are you looking at the half reaction table? Look at it. Because you cannot possibly write the correct reaction equation for this redox system if you cannot determine the formula for the stuff in the ferrous sulfate solution that contains iron. What is it? How many recognize this as the iron-containing ion in this solution? You see the formula for this ion in the half reaction table? In a few places, actually. You see this ion in the half reaction table? I mean, iron in this stuff is +2, so you can well expect it to form a well-defined hydrate. And these hydrates, as we've told you, are almost always octahedral. If they're not octahedral, we'll tell you what they are, because you otherwise couldn't know at this stage of the game. So all that's going on here is hydrated iron 2 is being oxidized to hydrated iron 3, while silver ion, AQ, is being reduced to silver metal. That's it. Look at half reactions 37 and 38 in the half reaction table. Does 37 not show you what I just said? Hydrated iron +2 is being oxidized to hydrated iron +3. And 38 shows the reduction of silver ion AQ to silver metal. That's all that's going on here. So you put together these two half reactions and recognize immediately that the net voltage for this system is plus 0.03 volts. Not much, but enough. All right. Part 8. An interesting compound of copper because it contains copper in the +1 oxidation state. The most common oxidation state by far of copper is +2. You'll see a number of half reactions in our table which contains copper in the +2 oxidation state, but a couple which contain copper in the +1 oxidation state, like this one. System 8 also corresponds to a process that electrochemists commonly call Otto redox. I wrote it on the board. Otto redox. All this term means is that for the redox reaction in question, the stuff which is getting oxidized is also the stuff that's getting reduced. Same stuff. Stuff which is being oxidized is also the stuff which is being reduced. In this system, copper 1 oxide, call it cuprous oxide, is being oxidized to hydrated copper ions, while cuprous oxide is being reduced to copper metal. And all this is taking place in 1 molar sulfuric acid solution. I've done this by demonstration, and it works quite nicely, but it's difficult to see because you're making this stuff in the presence of this stuff and in the presence of this stuff. So you got two different solids in there in the presence of a rather intensely colored solution. So it's hard to see what's going on. I mean, unless you're standing right over the beaker. And unfortunately, I don't have a big enough beaker where everybody here can stand over it at the same time. That'd be a hell of a big beaker. All right? By now, you should know enough about these rules to develop these half reactions. To make this, how many moles of water are required? 12, because we had to make 2 moles of hydrated copper ion if we're reducing a mole of this, because this has got 2 moles of copper per mole of compound. And we're operating all the time in water solution systems, so we got the water all over the place when we need it as a reactant. So here's another case where a -2 oxidation state oxygen is involved, isn't it? This is cuprous oxide. This is a -2 oxidation state oxygen. And when a -2 oxidation state oxygen becomes part of a chemical system, as it does in this case, what always gobbles up that -2 oxidation state oxygen? What's the answer that's always right? A strongest acid present in appreciable concentration or amount, Bronsted acid. And in sulfuric acid solution, we know that acid is what? Hydronium ion. How many hydronium ions in acid solution do you need to beat up 1 oxide ion? 2 of them. And when 2 hydronium ions clobber 1 oxide ion, what do you make? Water. How many moles? 3. So after we get this thing developed, 12 moles water reactants, 3 moles water products, so we can take away the 3 moles water products, and then just moles of water reactants to 9. Nothing fancy. We just took away 3 moles of water from each side of the reaction arrow. Remaining part, electrons. 2 moles plus this side. As things stand so far, 4 moles plus this side. So our multiplier's got to be 2, which of course keeps with the total oxidation state experienced by oxidation state change experienced by copper. 2 moles of +1 copper became 2 moles of +2 copper. Now, Otto redox. Cuprous oxide is also getting reduced to copper metal. Well, I've already established material balance for copper. Is this not another case of an oxide ion appearing to disappear? When oxide ion goes into a chemical system, it's always consumed by the strongest Bronsted acid present in appreciable concentration. So here we go again. Done. That's it. Now for part 9 and 10 and 11 and 12, those were all part of our redox demonstration. I will ask one question though, because one of these parts, I forget which one, is talking about the oxidation of potassium by water. When we did the redox demonstration, we looked at the oxidation of sodium by water. Vigorous, violent reaction. If I oxidize potassium by water, do you think it will be a more violent reaction or a less violent reaction than the oxidation of sodium by water? What I'm asking you is, which element do you expect to be the stronger reducer? Sodium or potassium? I'll give you a clue. You should have done this in 2045. Not with the specific question, but with the considerations that you need to make to answer the question. Sodium or potassium? Which do you expect to be the stronger reducer? I'm listening. Nobody wishes to venture a yawp? Which one is the stronger reducer? Sodium or potassium? Well, votes again then. How many vote for potassium? How many vote for sodium? Half a vote. Looks like about 50-50 split. So I got a feeling that most, if not all of you, are answering this by a mental coin flip. That ain't no way to proceed, not if you want to be successful. What property of elemental sodium versus elemental potassium do you need to pay attention to answer this question? Which one is the stronger reducer? Because what I'm asking you is, which of these is more easily oxidized? You remember a process in 2045 that I'm sure you considered from a trend standpoint, which showed Na becoming Na plus with electron loss compared to K becoming K plus with electron loss, and I'll bet you these were considered in the gas phase. What is the property that I'm referring to? What is it? What is it? What's this? Ionization energy. Did you learn about trends in ionization energy? You did that in 2045, didn't you? But did you, in learning these trends, attach the trends to explanation? K, 19 protons in the nucleus of an atom of K. Only 11 protons in the nucleus of an atom of sodium. Based on proton count, from which of these atoms is it more difficult to remove an electron? Based on proton count. K or Na? Based on proton count. K. You got 19 plus things holding on to a valence electron. But which of these atoms is more easily ionized? Because proton count is not the determining factor underlying properties of atoms like ionization energy. What is the determining factor? Why is K easier to oxidize than Na? Two atoms just floated in here. One's like this, softball. The other one's like this, volleyball. Which one is the volleyball? K or Na? K. K is bigger than Na, isn't it? And that's a determining factor. Even though you got more protons in the nucleus of K, the valence electron, 4s in this case, versus the 3s valence electron of sodium, is a good deal further removed from the nucleus. And Coulomb's law tells us charge times charge divided by d squared. What's a d term in the Coulomb's law? Distance. Distance between the charged particles. That force of attraction falls off as this distance squared. It means if you move the distance this much, the attraction force diminishes by that much squared. That's pretty big. That's why K is easier to ionize than Na. That's why if I put K with water, I'm going to get even more vigorous, violent reaction than I do when I put sodium in water. Interesting. Now, since we went this far, I might as well add one more statement to this analysis. What we talked about regarding trends for the oxidation of sodium, and then potassium, and then rubidium, and cesium, and even francium, if we want to fool around with this radioactive stuff, holds for the oxidation of these metals by water. Sodium is readily oxidized by water, but these metals get more readily oxidized by water as you go down the list, Na down to Fr. But which metal of family 1A is the most easily oxidized by water? It's lithium. How can this be? That's contrary to trend. What the hell is going on here? What is this mystery? How can lithium, which has got the highest ionization energy, most energy is required to take away an electron from lithium relative to the other 1A atoms. Yet lithium in water, mind you, is most easily oxidized. How can this be? Well, do you think it might have something to do with size? Li plus, Na plus. Tell me, for each of these single plus ions, if you're a water molecule, so for now, everybody here is a water molecule. Behave like one. Will you, the water molecule, with your squiggle minus oxygen end, stick more strongly to Li plus or Na plus? Which one? I'm listening. Come on, water molecule, talk to me. I'm listening. Metal ions with appreciable positive charge density form well-defined hydrates. Now, neither of these metal ions have appreciable charge, but one has a much greater appreciable positive charge density. Which one? Lithium. They're both +1, but the Li ion is a lot smaller. And that's why lithium is the strongest reducer of water. Now, bets are off when you go to a different oxidizer. But in water, the hydration energy that's liberated when Li plus is formed and interacts with water molecules more than compensates for the additional energy you have to pay to take away a single electron from the lithium atom. Now, that's a lot of stuff. And what we just said is nothing I would hold you responsible for on a quiz or exam. We haven't paid attention to it in detail. But it's good chemistry. And if we had the time, we'd take a look at this very case in greater detail in chapter 23. In any case, Back to half reaction considerations. Let's now talk about the chemistry of a rather common system, a system which I bet each and every one of you owns. Everybody got a car? Everybody got a battery? In the car. You don't have a battery, how the hell are you starting this car? You got an old Model T like this here? Chemically, the lead storage battery is very simple. It's composed of lead, metal, lead dioxide, which has got lead in the +4 oxidation state, which you should recognize at a glance, and the electrolyte is 4.5 molar sulfuric acid solution. So beside lead and lead dioxide, you got hydronium ion, principally hydrogen sulfate ion rather than sulfate ion. And of course water. That's it. So if with these chemical components of the lead storage battery, I tell you that at each electrode in the lead storage battery, the anode and the cathode, the anode being the electrode at which oxidation occurs, the cathode being the electrode at which reduction occurs, if at each of these electrodes lead sulfate is produced, it's produced by reduction and it's produced by oxidation, can we develop the half reactions and then the net cell reaction and then couple them together in order to get the net cell reaction for our lead storage battery? The answer is you're damn right, so let's do it. Since in the analysis of electrochemical cells, you read the cell from left to right with the anode written at the left, we'll start with developing the anode half reaction first, the electrode at which oxidation occurs. So if we know that lead sulfate is produced at each electrode, we can start with this. Lead sulfate's a product, and this is the half reaction which shows oxidation, so electrons are also part of the products. What's getting oxidized? Lead. What else could be oxidized? Principal species inventory tells us that the sulfate containing source is hydrogen sulfate ion. I'll use the condensed formula just to save room. So look at what we've got so far. We see lead being oxidized in the presence of hydrogen sulfate ion, and the lead converts to lead sulfate. Well, that means hydrogen sulfate has got to lose H+ in this process. And when H+ is lost in a process, when H+ is contributed to a chemical system, what always gobbles up the H+? The strongest base present in appreciable concentration or amount. Tell me, what is the strongest base in this system? Water. I want to move this over a little bit. And when water gobbles up H+, as we know, we're making hydronium ion. Now we have established material balance for the chemistry that occurs at the anode in the lead storage battery. The oxidation part of the chemistry of the lead storage battery. Remaining part is established charge balance. As things stand, we got a mole of plus on the right and a mole of minus on the left. That means we got to have for a multiplier what? Does that not keep with total change in oxidation state experienced by lead as it was oxidized in this process? Lead became lead plus 2. All right, we go to the cathode. Now we start with this. Again, we know lead sulfate is a reaction product, specifically in this case the reduction product. And since this half reaction will correspond to reduction, it's got to be an electron consuming half. What's getting reduced? Yeah. This has got lead in the plus 4 oxidation state. So here we are again with a system where minus 2 oxidation state oxygens are being chewed up. What are these minus 2 oxidation state oxygens being chewed up by? Plus, we again made a sulfate containing product. Well, given that we made a sulfate containing product, that obligates us to realize that hydrogen sulfate ion has got to be a reactant. Because it's only principal species sulfate containing stuff in the pot. So to finish this puzzle, we've got to determine the fate of these so-called disappearing oxygens, minus 2 oxidation state oxygens. Call them oxide ions, so we can recognize how they behave chemically in this system. We answered this a moment ago. If a reaction runs and contributes minus 2 oxidation state oxygens to the system as the reaction runs, what's going to eat up these minus 2 oxidation state oxygens? The strongest Bronsted acid in the system in appreciable amount or concentration. And in this system, what is that strongest acid? Hydronium ion. But be careful, because in this system, in addition to hydronium ion, as this system runs, we are putting an acid into the system which is stronger than hydronium ion. We're putting an acid into the system that's stronger than the sulfuric acid molecule. That's number 2 in our acid column. We're putting an acid into the system that's stronger than perchloric acid, which is the strongest acid listed in our acid base table. In fact, the acid we're putting into the system as this reaction runs is the number 1 strongest Bronsted acid of all. What is this acid? The number 1 most powerful Bronsted acid. What is it? I'm listening. On your paper right now, I want you to write the formula for the number 1 strongest Bronsted acid, period. There ain't none stronger than this Bronsted acid. What is this acid? There it is. That's what Bronsted acid chemistry hinges on. The transfer of this thing. That's number 1. H plus all by itself. In this system, where's this H plus coming from? As this reaction runs. Where's this H plus coming from as this reaction runs? Coming from here. Because this stuff in reacting with this stuff to make this stuff creates H+. Now, in truth, there's no free H+'s floating around in here. In truth, hydronium ions are a stronger acid than hydrogen sulfate ion. But you have to realize, as this reaction runs, conversion of this to sulfate ion puts H+ in the system. So H+ produced by deprotonating hydrogen sulfate ion gives us 1 mole of H+'s to provide protons to attack these oxide ions. How many total H+'s do we need to convert these oxide ions in acid solution to what product? Water. So beside the mole of H+ we got from the mole of hydrogen sulfate ion, how many more moles of H+'s do we need? 3. What are we getting these H+'s from? Hydronium ions. So the remaining part is, how many waters are we making? How many? We pulled H+ from 3 hydronium ions, and along with the H+ we got from the hydrogen sulfate ion, we converted 2 oxide ions to water. 5. You do have to be able to count. So our electron multiplier is 2. Just like it was for the anode half reaction. Because again, for this half reaction, lead is experiencing an oxidation state of change of 2. Here it went from 4+ to 2+. Now, let me give you some data. E0 for the anode half reaction is plus 0.36 volts. E0 for the cathode half reaction, I erased cathode because I needed the space, is plus 1.68 volts. Now the tough task is adding these up. You get plus 2.0 volts. The question is, your car battery. Contains how many of these lead cells coupled together in series? How many? Louder. 6. Damn right. 6 times 2 is 12, isn't it? Does your car battery deliver 12 volts if it's working properly? Huh? Yeah, how about that? You know how to get the net cell reaction. Now, let's take a look at, to finish this conversation on half reactions, Q's 22, 16, and 17. Which follow from, the answers to these questions follow from the analyses we've just done. $16. Well, we better hold on 16 because that requires reference to the information at the top of page 2218, and I've decided that information is somewhat out of place. So we're going to take this information at the top of page 2218 and advance that into our conversation tomorrow on the Nernst equation. We're going to forget then question 16 and just do question 17 here. Question 17 has a couple of parts. The first part says, zinc is a poorer reducer than potassium. If, based on the analyses we've just done, I asked you to defend this statement, that zinc is a poorer reducer than potassium, what would you write down? Because I'm going to ask you stuff like this on the exam at the end of this week. What experimental results have we considered during this analysis, or these analyses, to say flatly that zinc has got to be a poorer reducer than potassium? What experimental results have we discussed to support the conclusion that potassium is assuredly a stronger reducer than zinc? If we put zinc in water, what happens? Nothing. You put potassium in water, what happens? Get the hell out of the way. Boom. Well, if this is the oxidizer, and this can murder this oxidizer, and this does nothing, then this must be a stronger reducer than this. Next part. Hydronium ion is a stronger oxidizer than nitrate ion. What results did we look at last time when we did the redox demonstration that allows us to say flatly that hydronium ion is a stronger oxidizer than nitrate ion? Or, if you don't remember that, look back in the notes at question 15. Number 11, part 11, I'll read it to you. Zinc does not react in 6 molar sodium nitrate solution, but reacts readily in 1 molar nitric acid solution as hydrogen gas leaves the system. You remember what we did last time during the redox demonstration? We found out that copper, which is not oxidizable by 9 molar sulfuric acid solution, is readily oxidizable by 6 molar nitric acid solution. And in so doing, we realized that nitrate ion was the stuff that got reduced, in fact, to nitric oxide, NO. Well, we wanted to know if nitrate ion could do the job by itself. So we put copper in 6 molar sodium nitrate solution, nothing. And the copper in 9 molar sulfuric acid solution, nothing. So we concluded we needed nitrate ion, but hydronium ion also to support this redox process. And then we got the copper to be readily oxidized with the hydronium ion nitrate ion combo, with each of those present in high concentration. Now what part 11 of question 15 tells you is that zinc does nothing in sodium nitrate solution, but goes readily in the presence of hydronium ion. That's enough said. If hydronium ion can oxidize zinc at 1 molar and nitrate ion at 6 molar cannot, hydronium ion's got to be the better oxidizer. The last part is silver, 1 molar hydronium ion and hydrated copper ion. If we tell you that silver with hydrated copper ion is no reaction. Silver with hydrated copper ion is no reaction. Notice I'm also telling you with this statement that copper is a better reducer than silver, and hydrated silver ion is a stronger oxidizer than this. This tells us that. Silver does nothing with hydrated copper ion. How does that support the conclusion that silver in the presence of hydronium ion ain't going no place? To jog your memory. What did copper do in 9 molar in 9 molar sulfuric acid solution? What did the copper do? It didn't do a damn thing, did it? Well, if copper has now been found to be a stronger reducer than silver, and copper can't reduce hydronium ion, can silver reduce hydronium ion? Hell no. No way. But now let's throw a ringer in there. What if I put silver in this acid solution? Do you think I have a much better chance to oxidize silver if I put it in this acid solution? Does this have 1 molar hydronium ion? What else does this have? Chloride ion. Does silver show a tendency to react with chloride ion that copper does not? What is that tendency? What do you know about the solubility of silver chloride? How about that? We'll pick it up from this point tomorrow.